We present our latest work on Affordance-Aware handovers, considering human arm mobility constraints. In assistive scenarios where people have arm mobility limitations or as we grow old and lose arm mobility and stability, it is important to have a carer that considers minimizing the effort of the receiver when handing over objects. In our proposal, we minimize the receiver effort to take and to use the object afterwards. Propose a heuristic cost that hierarchically optimizes robot grasps depending on the receiver's upcoming task as well as the object poses to adapt to users with low arm mobility capacities. To extract preferences of handover methods across users with different arm mobility levels, we present our cost model along with other state-of-the-art methods in handovers in a user study. The extracted preferences are then encapsulated in a statistical relational learner, on which we query the appropriate handover, composed of robot grasps and an object pose, that adapts to what the user inputs as their arm mobility capacity and upcoming task. Per method, we show the participants 5 different objects. Considering these 3 methods, we start with the hypothesis that people with low arm mobility will prefer a handover technique that requires less effort from the receiver. Using nature and neurophysiology literature, we calculate the effort per joint of the simulated human in our animations, corroborating that using our method, the effort on the joints is less than the average when using the state-of-the-art method. To collect opinions from users with different arm mobility capacities, we asked the support of the Chest, Heart, and Stroke Scotland, from where we got 9 volunteers, and also we paid 250 participants from Mechanical Amazon Torque. In the first part of the study, we follow studies that present different arm mobility levels and allow the users to identify themselves with one of the animations. In summary, we found out that people with lower arm mobility prefers a method that brings the object closer to their arm, while people with higher mobility prefer some freedom and to reach the object somewhere in the middle. In terms of what users consider to be the most important factor in handover tasks, high and low arm mobility levels have almost opposite views, where for high mobility it is most important to feel safe in the presence of the robot, and for lower levels of mobility, it is most important that the robot tries to do most of the motion when in a handover task, where people with high arm mobility consider the help of the robot with conditionals. People with lower arm mobility perceive the robot as a help. Using the collected preferences from the user study, we learn a reasoning model. In this way, being able to generalize handovers given the user's arm mobility and upcoming task. Using an external camera, we detect the human location. We use this information to plan and execute the handover in simulated and real scenarios.